Hello everyone, this is our last lesson for Unit 5. This is writing exponential functions from the real world. This is not unlike writing exponential functions that you've seen. This time it's just from a word problem or a real world situation. We're still going to have that same equation, that y equals a times b to the power of x. And so we're still going to need to identify that starting value or amount, that a value, and we're going to need to identify the growth or decay rate, the b value. Then we're going to have to substitute into that equation. So same idea, we're just going to get the information instead of from a table or from a graph, from a word problem. So let's review. An exponential function is just the equation y equals a times b to the power of x, or you may see it written y equals, or even f of x equals a parentheses, which just means times b to the x. Both of those are going to show you that we are dealing with an exponential function, key being this x is in the exponent. With exponential functions, we are talking about exponential growth or exponential decay. A great example of a real life situation is population growth. So over here on the right, you have this lovely picture. You start with one person, right? And then you move. They get married. Maybe you have 3 kids. So just from those, 1 plus 1 people, right? You start with 1, you become 2 when you get married, or you have a kid with someone else and you have kids. And then each of those 3 kids go on to have their own families. And then those kids have their own families. And so the story, the population, your family is going to grow the farther along you go along the generations, right? If I start with my grandparents, there was just the 2 of them. My grandparents had 4 kids. Those 4 kids had 2 kids, 0 kids, 3 kids, and 4 kids. And that is down to me, and each of me and my cousins are going to have who knows how many number of kids, but it's going to be bigger than that 2 that we just started with my grandparents. So population growth is growing any kind of population, not just humans, but animals. That is an exponential function because we're not growing at a steady rate. You might hear it say we're growing exponentially by a growth rate. Okay, in the same note, that is also how we decay. If things decay, it's a decay rate. But if you think literally, like, what does it mean to decay? That. The decaying process starts slowly, but as it goes, it's growing in size and how fast it decays because it's already decayed. Okay, so I think that's just really cool, and that's why exponential functions is so important. It's very, very, very real life applicable. So we'll get to see that in some of our examples today. Just a couple of reminders about the a value. What's the a value? It's the starting value or the starting amount or the initial value. It's the y-intercept. But in terms of real world problems, we want to think in terms of starting value, initial amount, whatever. And again, it is that y-intercept, but when we're talking about real world problems, you're going to see it written as like the first number, or we start with this much, or this is the highest it could be, something like that. And that b value is our growth or decay rate. And we're going to see growth and decay rate in 2 different forms today. We're going to see it where we're given the growth or decay rate, and then we're going to also see it given as a percentage. When we're given it as a percentage, we're going to need to do some extra math in order to plug it in, but we'll cross that bridge when we get there. Right now, let's just talk about growth. Remember, growth is if the b value is greater than 1. Anytime you have a growth, it needs to be greater than 1. And then the decay value, your b value is going to be between 0 and 1. Right? Remember, growth looks like this, and decay is looking more like that, the opposite way. So let's look at when we're given the a and the b values initially. where all values are given. Example number 1. When rabbits were first brought to Australia in the 1800s, they had no natural enemies, so their number increased exponentially. Assume there were 20 rabbits first brought to Australia, and the population doubled each month. Well, first of all, what's the initial value? Well, there were 20 rabbits first brought. That's what we started with. That's our starting amount. What's the growth and decay rate? Well, what happened to the population? The population doubled each month. What does it mean to double? It means to multiply by 2, which means our growth rate is 2. How do I know it's growing and not decaying? Because this value is bigger than 1. So my last step, after I've identified the initial value and the growth or decay rate, I just plug it into the equation. So y, or f of x, I'm going to do f of x here. F of x equals my a value times my b value to the power of x. And there you go. Let's look at example number 2. In example number 2, in 1990, the population of the U.S. was about 260 million. During the early 1990s, the population of the U.S. was changing at a rate of 1.02 annually. Suppose that the growth rate remains constant. So let's identify the A and the B. Well, what's the number we started with? Okay, we're not talking about years here. We're talking about the population, right? So what was the population? Oh, the population was about 260 million. So that initial value, 260 million. What's the growth or decay rate? Changing at a rate of 1.02. So if my growth or decay rate is 1.02, is that growth or decay? Well, once again, that value is greater than 1. Just barely, but it is. So it's going to be a growth rate. It's going to be growing. Okay, sometimes you'll see a keyword in there. It'll say, instead of changing at a rate, sometimes it'll say growing at a rate or decreasing at a rate. It'll tell you what's happening. And that's going to be important in in our next little section here. Okay, but writing the equation, we just need to plug it in. 260 million times 1.02 to the power of x. You're going to see me use parentheses a whole lot more than just writing that little dot for the multiplication symbol like we looked at initially, just because it's a little bit more cleaner and clear cut. As long as you remember it's multiplication for exponential functions and the exponent is in the, or the exponent is the x variable, then you're going to be good to go. So this is when all values are given. You should be able to find the growth or decay rate and the initial value given to you. This is one type of problem, a real world problem that you would see. And we can use these equations that we've come up with to find out the population after a given number of months or years, depending on what the time frame we are looking in. Now let's look at what happens when we're increasing or decreasing by a percentage. So it's not going to give us the actual growth or decay rate. It's just going to say it's increasing by this amount, this percentage per year, or by this percent per year it's decreasing. So what do? We're going to have to find B. We're going to have to find B. The percentage is not B. Okay, maybe make a note of that, right? Percentage is not the B value. But it is part of the B value. So let's take a look at example number 3, and I'll show you what I mean. The starting salary for a new employee at the Thrifty Federal Credit Union is $25,000. The salary increases by 3% each year. So, starting salary, $25,000. Let's use pink this time. So $25,000 is our initial value, that's starting amount. But what's the growth or decay rate? Well, it gives us a percentage. This percentage is not the rate. But to find the rate, we need to either take the number 1. Wow, why is it doing that lovely line there? And add or subtract the percentage from it. Luckily, we can use our calculator to help us. There's a percentage button on the calculator, and if we just type 1 plus or minus, depending on what we want to do, the percentage, in this case 3%, it's going to give us the value, the actual B value. We could also change the percent to a decimal, like I'm going to show you here, and add or subtract it. Here's where growth and decay is going to be really important, making sure you understand which one. So we already came up with a starting salary, right? We know that's the initial value. The growth or decay rate, we know it's by 3%, but what is it doing? Is it increasing or decreasing? It's increasing, which tells me it should be a growth, which means when we use this that I've just boxed here, we need to make it be bigger than 1. So we're going to add that 3%. So either you can type in this 1 plus 3% into your calculator, or you can do 1 plus 0.03 because that's 3%. Either way, you're going to get 1.03. This should be greater than one because it's increasing. So it's a growth rate, not a decay rate. That's how you can kind of check your work is it following this rule here at the beginning, these growth and decay rules? Is it bigger than 1 or is it between 0 and 1? So now that I have the A and the B values, I can plug them in. Y equals 25,000 times 1.03 to the power of X. X in this case is time, lots and lots and lots of times with exponential, you'll see it's time. It's increasing by 3% each year, so years is where the X is. So in that question, what would an employee's salary be after 5 years? We just take our equation and use our calculator to help us. So I'd be typing this in the calculator, and instead of putting an X, I'm going to put a little 5, so to the power of 5. Type that in our calculator, and we're going to get our answer. 28,981.85 should be what you get. That should be the salary after 5 years. Okay, all you have to do is plug it in, and so you can see that for finding out money and things like interest, things like that, they're similar. Compound interest, for sure, similar to exponential functions. Let's take a look at example number 4, and then be sure to ask your teacher if you have any questions while you're working, because this can be a little bit confusing. You don't want to switch up your A and your B values. Talking about my favorite animal here, in 1980, there were 1,200,000 elephants living in Africa. The number of elephants has decreased by about 6.8% per year. So in 1980, there were how many elephants? 1,200,000. So that is our initial value. That's how many elephants we started with. And the growth or decay rate. It says it's decreasing by about 6.8%. So that's going to be a decay rate. And that means when we look at that 1 plus or minus the percentage, okay, that's how to find the B value. We are looking at 1 minus the percentage. So 1 minus 6.8%. That is going to translate to 1 minus 0.068 if we change that to a decimal, which again, you can just type this initial part into the calculator and you'll be golden. And you'll get your actual B value, which should be between 0 and 1 since we're decaying. 0.932 is in fact between 0 and 1, so that is our decay rate. Now we just need to plug it in. 1,200,000 times 0.932 to the power of X. And once again, we can use that then to calculate how many elephants there will be in any given year. So remember, we started in 1980. I think that should say 1996. We can't go back in time. So let's make that be in 96. That makes more sense. In other words, from 1980 to 1996, how many years happened? 16 years. So in 16 years, what happened to the population? How many elephants now are there going to be in 1996? Or were there, since that happened already? So once again, let's just plug in the number, and instead of putting an X, we're going to plug in 16 right there for that X. Type it into your calculator and then come back with the answer. Totally realized I forgot a 2 there. It should be 0.932, not just 0.93. Didn't forget it on purpose. 16 years later, the population went down from 1,200,000 to 388,898 elephants. That is a vast number of elephants decreasing. Okay, so pretty straightforward, especially when you are given all the values. Where you have to be tricky is where you're given a percentage. You need to either, again, to get your B value, take the percentage and add it to 1 for growth, or for decay, subtract the percentage from 1. Either way, it's going to be revolving around 1, but that's going to get you, remember, B being greater than 1 or between 0 and 1. Okay, let your teacher know if you have any questions.